Hello YouTube and welcome to this exciting new machine learning tutorial in Python. I'm Ryan from Stemplicity. I'm a professor and passionate YouTuber. I'm super passionate about teaching machine learning, coding, and AI in a simple, easy, and fun way. I've taught over 45,000 students from over 150 countries. Please subscribe to my channel for more videos. In this tutorial, we will teach you the basics of machine learning and we'll apply them to a practical project in the fintech industry. So before we start with our tutorial, let's start with a simple question. Why do we need to study machine learning? Well, machine learning is one of the hardest skills to acquire this year. The total number of machine learning jobs over the past 2 years has grown over 600%. The field is exploding with opportunities, and there are new discoveries made every single day. This tutorial will cover the basics of a branch of machine learning known as classification. You can think of this as we want to know if a patient has, let's say, diabetes or not. Is it going to rain today or not? You got the idea. In this exciting tutorial, we will build a classifier model to predict whether a customer at a bank is ready to retire or not. We will ask customers some questions and we'll get some features from them, such as their age and their savings, and we'll be able to predict whether they are eligible to retire or not. This tutorial will not only teach you the theory behind machine learning, but will teach you how to effectively build our model using a famous Python package known as scikit-learn. Without further ado, let's get started with this tutorial. Hello everyone and welcome to this section. In this section, we're going to cover the support vector machines, which is a very famous classification algorithm that we're going to be using to classify data points or data sets. And so the order of mainly the section, we're going to start with the support vector machine intuition, and we're going to go ahead and cover two major projects that we're going to apply support vector machines from scratch, including importing the data set, cleaning up the data set, and actually applying the support vector machines in action. All right, so let's go ahead and cover the support vector machines intuition. Let's assume that you are a data scientist who is working at a major bank in New York City. All right, and as a data scientist, you are working with other bankers, and what the bankers do in general is that they sit with people or customers, and they try to collect data about their age, okay, and about their savings, which is what we call it, let's say 401k savings, which is one of the savings plans in the United States, where people look at their retirements, try to save money for their retirements, where they can use it after they reach age of 60 years old, for example. So what you're looking for, that you wanted to classify a new clients as eligible to retire or not, given their customer features. So simply put, customers come, they provide you with their age, if they are, let's say, 30 years old, 40 years old, 50, 60, 70, or whatever. And they will provide you with the savings amount, which is their amount of dollars saved in their 401k retirement. So simply we have two features. Here we have feature one, which is the age. Here we have feature two, which is the savings. And simply we have two mainly kind of classes, okay? The first class, which is the red class that we have here, is that people who are not eligible to retire. And here we have our gray class, which are people who are eligible to retire. All right. So what we're trying to do is, instead of asking or letting the banker decide on their own based on this, we're just going to get all the data points, train a model that can simply, we're going to provide it with the age, with the savings, and it can predict for us, if that customer is eligible to retire or not. Okay. All right. So the question is here, how can we separate these two classes? That's what we're looking for. So the first question is, okay, maybe this line would work great. Maybe this line would be able to classify or separate these two classes together. All right. Maybe somebody will say, okay, maybe not that line. Maybe this line would be able to separate these two classes from each other. Someone might say, no, maybe this might be able to classify these two classes or like separate them. And that's where the power of support vector machines comes into play. Support vector machines try to simply use what we call the support vectors, which is these 2 points in here. Okay, I'm going to tell you exactly what they mean by support vectors. to try to find what we call it the maximum margin hyperplane. Again, what support vector machines is trying to do as kind of an algorithm, it's trying to find that line in here which is perfectly separate these two classes from each other. This line is what we call it the maximum margin hyperplane. Okay? And these two are kind of this distance in here is what we call it the maximum margin. And these 2 points is what we call it the support vectors. All right. So what do you mean by this? In a nutshell, what support vector machine is doing is it's trying to find these 2 points on the boundary, which is like these 2 points are kind of hard to classify them as either retired or not. They are in the boundary in here. They might be even closer to each other. And what support vector machine is trying to do is trying to find what we call the maximum margin hyperplane, which is that green line that perfectly separate the two, so that the distance in here between these two, between the first class or the first support vector and that maximum margin hyperplane, and this distance in here, which is between the support vector of the other class and that maximum margin hyperplane, kind of will be equal and will be maximized in a way. So we're trying to maximize that distance in a way, kind of push that line away from here, push that line away from here, so we can perfectly separate the two classes from each other. All right? If you guys don't get that, I have kind of a more detailed example that can walk you through what do we mean by the support vectors. Let's assume that we wanted to, for example, classify images of animals to either cats or dogs. All right? So these class, all the gray points, these are the cats. Here, all these red points are the dogs. All right? So if we take a look at it, you will find that here, these 2 features might be, let's say, for example, like the size of the nose, for instance, and maybe the size of the ears, okay? Think of these 2 features as something like that. So this point, okay, is what we call it the perfect cat. Because of the feature 1 and feature 2, this point is really difficult to be classified as a dog, which is, you know, if you take a look at the picture here, it looks, you know, like looks exactly like a cat. You know, like nobody will ever say, okay, no, this is a dog. This is like kind of a perfect 100% cat, which is with a very high accuracy, okay, or a very high kind of, you know, like confidence. And that's why these points are really far in there. They are pure cats. These points, they are really far to the left-hand side, and they are pure dogs. Okay, their features are exactly a dog. Like looking at that picture, it looks like a perfect dog. However, in here, these 2 points are like something like this. You know, it's like I found that a picture actually on the internet. It's kind of, you know, like it's really difficult to tell. Is this a cat or is this like a dog? All right, and that's what we call it the supported vectors. So what the support vector machine's algorithms does for classification, it simply goes to these points on the boundary. They have kind of very mixed features. They are not pure gray. They are not pure red. They are something in between. All right. And they try to look for these 2 support vectors and try to find that hyperplane or the maximum margin hyperplane, which is perfectly separate these 2 features. And that's the power of support vector machines. You will actually find that when we apply the support vector machines in action, you will find that the actual classification results are great. Why? Because it only goes to the maximum or to the extremes and try to classify them based on these 2 support vectors. All right? Okay. I hope you guys were able to right now understand what do you mean by the support vectors, okay, and what do you mean by the maximum margin hyperplane. All right. So what happened is here is that we have, this is our trained model, is what we call it the maximum margin hyperplane in here. And in general, when we try to evaluate our model, we simply do 2 steps. We actually covered that before. Here, I'm just repeating it again. We use these points mainly for training. So we're actually going to feed the algorithm, what we call it X-train and Y-train, including these 2 classes. All right. And what happened is after we train the model, which is after we obtain our maximum margin hyperplane in here, we are going to use different data points. And these green points are what we call it the testing data set. We pass the testing data set in here to try to test our model afterwards, after we perform the training. Okay, and that's pretty much the process we're going to be following. We're going to take all our points, divide them into 2 categories: training and testing. The key element is that training data sets, these are data points, which is our green data points here, that have never been used or seen during training. So, which means when we train the model, when we try to obtain that straight line in here, we have to make sure that these data points were never being fed during training. They are completely new data points, never been seen by the algorithm, and that's how we can test the algorithm generalization capability. Its ability to actually classify new data points that has never been seen before during training. All right, okay. That's pretty much all the intuition for the support vector machines. Obviously, there's a lot of mathematics. If you guys are interested, you guys can access these two books. The first book is what we call it Understanding Machine Learning from Theory to Algorithms. And the other book is what we call it An Introduction to Statistical Learnings in R. And these two books are free, so you guys can access them here. So I included the link for the first book. This is the link for the second book. And if you go to page 202 in the first book, or page 337 in the second book, actually have them open in here, you guys can get more understanding of the support vector machines in way more details. So here, for example, the first book, this support vector machines. Again, if you scroll down, that's page 338. You will find, the definitions of what do you mean by a hyperplane, how can we find the hyperplane. Obviously, the hyperplane is the best line that can, classify these two points, the blue and red. And here it's showing you how can we obtain that, all the mathematics behind it, which line would be perfect fit, and so on and so forth. Obviously, there's a lot more details in here. I'm not going to dig a little bit into the mathematics, tons of mathematics behind it. I'm just going to walk you through the intuition. And then afterwards, we're going to take a look at the practical applications into how can we apply support vector machines in action. All right. If you go to the second book, which is Understanding Machine Learning, if you go down to page 202 and 203, you will find that there is an entire section for support vector machines, going through all the details, how can we select the support vectors, and how to do all the mathematics behind it as well. Again, if you guys are interested, all that is purely optional. We don't need it actually to understand all the details behind it, because in this course, we're going to take a look at the support vector machines from a practical perspective. All right. Okay, let's recap what we have done so far. So in this section, we're able to cover the intuition for support vector machine, and the idea of how can we find the maximum margin hyperplane, which is the line that can perfectly separate these two classes. And to do that, we use the support vectors, which is, again, points or data points that are on the boundary. They are very difficult to kind of classify them purely as class A or class B, which is either retire or not retire in this case. And here we took a look as well at kind of an overview of this is a pure cat, this is a pure dog, this is kind of in between, maybe cat, maybe dog, and these are the support vector in here. And these again, images that have kind of mixed features. They are very difficult to classify. And that's why when we apply support vector machines, we use these two mainly points to find the maximum margin hyperplane, which is a perfect line that can separate completely the two classes from each other. All right. Okay. And we also take a look at how can we use the training and testing data sets into our model. And also here, if we have an additional reading material. I hope you guys enjoy this lecture and see you in the next lecture. Hello everyone and welcome to this lecture. I hope you guys were able to figure out the project yourself. And if not, or if you got stuck, don't worry about it. In this lecture, I'm going to walk you through the detailed video explanation of all the steps needed to apply the support vector machines to the bank customer retirement predictions. All right, let's get started. So let's go ahead to the problem statement. Again, we assume that you work as a data scientist at a major bank in New York City, and you have been tasked to develop a model that can predict whether a customer is able to retire or not based on his or her features. Features are his or her age and net 401k savings, which is kind of your retirement savings account in the US. And you thought that, actually that might be, and you thought that support vector machines can be a great candidate to solve the problem. All right. First, we're going to go ahead and import the data set, and then we're going to visualize the data, and then we're going to perform model training, and then we're going to do model evaluation or model testing, and we're going to do the confusion matrix along with the confusion report, with the classification report. And then we're going to improve the model by performing normalization maybe, or maybe by doing the grid search afterwards, which is kind of the second improvement that we have done to the cancer case study. All right, I hope you guys were able to figure this out. If not, let's get started. So first step is we're going to import all the important libraries. So we're going to import pandas as PD, and we're going to import numpy as MP, and we're going to import seaborn as SNS, and as well import matplotlib .pyplot as PLT. Let's make sure everything is running. Okay, looks good. Let's actually delete all this just to avoid any of that confusion here. And let's go ahead and load the data set. So if you guys remember, all the data is contained within our support vector machine column folder here. So we have bank customer retirement CSV, right? So let's do that. So we can say, okay, bank underscore data frame equals to PD dot read underscore CSV. And we're going to pass along our bank underscore customer underscore retirement dot CSV. Looks good. Let's run that. Okay, looks good. Let's take a look at bank data frame. And here we go. Here we have simply customer ID, which is, indicating the customer, mainly kind of maybe bank account in there. Here we have our age, all right, and our 401k savings. And we have a column for retire. Either, you should be allowed to retire or not, which is 0 or 1, indicating retired or not. All right, let's take a look at our bank underscore data frame dot keys. We have done that before, obviously. And here we have customer ID, you have age, 401k savings, and retirement account. And if we take a look at the shape, so we have bank underscore data frame dot shape. We have 500 data points, so we have 500 rows by 5 columns. All right, looks good. So I'm going to ask you guys to do here is, to pause the video. This is a quick mini challenge. I want you guys to go ahead and plot or view the first 10 samples and the last 10 samples using the head and tail within the data frame. Please go ahead, pause the video, and I will see you guys after the challenge. All right, I hope you guys were able to figure out the challenge. So what I ask you guys to do is to view the first 10 samples. So we're going to say bank data frame dot head, and we're going to pass along the first 10 samples. Let's run that. And here we go. These are the first 10 samples. And I ask you as well to view the last 10 samples. So bank data frame dot tail, and we're going to pass along 10 as well. And here are the last 10 samples we have from 490 up to 499. Okay, looks good. And that's pretty much the first step into importing the data. The next step, I wanted to simply use seaborn pair plot to actually visualize the data. I'm going to say, okay, SNS.pairplot. I'm going to pass along our bank underscore data frame. We're going to pass along our hue. We're going to be our retire column, which is simply our retire column here. This is our column here. Okay, that indicates are we retiring or not. And we're going to pass along our vars. Apologies, here we're going to pass along our variables. We're going to be we need to plot the age. And we want to plot our 401k savings as well. 401k savings. All right, let's run that. Obviously, something is not right. Obviously, bank DF. And here we go. All right, looks great. So now we have our age, our 401k savings. So it seems as you increase the age as you get older, and obviously if you have more retirement savings, you are class 1, which means that you are eligible to retire. So which means the model should predict that you are okay, you are good to retire because you're pretty much older and you have much more savings. And if you guys take a look here, you will find that the mean of the people who are willing to retire, first of all, regarding from the age perspective, is around, let's say, 55 per se. And people who are not allowed to retire are younger crowds, right? So around 40, give or take. Regarding savings, if you have $750,000 saved, you are eligible to retire. If you have around, let's say, $250,000, you are not eligible to retire yet. All right, let's go ahead and do the count plot as we have done before. So we're going to do SNS.count plot, and here we're going to pass along our bank underscore data frame, and we need to basically count the retire column, and we can label this as, let's say, retirement. Okay, let's run that, and here we go. So the data is pretty much balanced. So we have, around 250 samples for retirement and 250 samples for non-retirement. All right, and that's pretty much step 1 and 2, how to import the data, how to visualize the data. And in the next section, I'm going to walk you through how to perform model training and how to do model evaluation as well. I hope you guys enjoyed this lecture, and see you in the next lecture. Hello everyone, and welcome to this lecture. In this lecture, I'm going to walk you through the model training. So in the previous lecture, we walked you through the visualization of the data. So we're able to visualize the data in here. We realized that we have mainly 4 columns: customer ID, we have age, we have 401k savings, and we have kind of the target class, either to retire or not. All right, and in this section, let's go ahead and perform the actual training. So we're going to say, okay, our bank underscore data frame going to be equals to our bank underscore data frame dot, my apologies, underscore data frame dot drop. First, I don't need the customer ID. We're not going to be using it anywhere. It doesn't mean anything for us. So I'm going to say we're going to drop that, and let's go ahead and actually drop it. So we're going to say, okay, drop, go here and indicate customer ID. And we're going to specify axis equals to 1 to remove the entire column, basically. And that's the first step. Okay, looks good. And let's take a look at bank df, bank underscore data frame. Here we go. So now we don't have the ID anymore. The next step is to, again, if you guys recall, we're going to use the X, which is the inputs. We're going to use age and 401k savings as input. And we're going to use the retire as an output. All right, let's see how can we do that. So we're going to say, okay, let's drop the target label. So we're going to say X equals to our bank underscore data frame dot drop. So we're going to drop that. And here we're going to use the retire column as drop, and axis we're going to be equals to 1 as well. So I don't need the retirement column when we're actually using the input to the model, which is our X column. Let's run that. Let's take a look at X, and here we go. Here we have our age and 401k savings. Looks perfect. The next step is we wanted to drop the retire. We're going to use the retire column and set it to Y. So Y will be equals to our bank underscore data frame, and we're going to pass along our retire column. Let's run that, and let's take a look at Y. And here you go. That's our Y, which is basically a bunch of zeros and 1, indicates whether you are eligible to retire or not. Let's go ahead and maybe visualize our X dot shape, which is, again, we have 500 by 2, right? And let's take a look at Y dot shape. Here we have 500. Okay, looks great. Let's go ahead and delete all this just to avoid any confusion. And let's go ahead and do the train test split. So we're going to say, okay, from sklearn, we're going to do dot model underscore selection. We're going to import train underscore test underscore split. Okay, looks good. And then we're going to say, okay, X underscore train. We're going to say X underscore test. We're going to say Y underscore train and Y underscore test equals to train. If you do tab, that should complete. Tab auto complete, train test split. And here we're going to pass along our X value, our Y value, and our test size. And here we're going to set it to, let's say, 0.2. We're going to set it to 80%, 20%. And we can specify random state here. Random state equals to 5, indicating that basically when you set random state to 5, you're going to get the exact same result as mine. All right, let's run that. All right, looks good. Now we divided them. Let's take a look at X train now. Dot shape. This is our xtrain.shape. So now we simply divided the data set into 400 data for training and 100 data for testing. Let's take a look. So that shape, here we have 100 data points for testing. All right, looks great. Let's take a look and make sure that y-test as well looks great. So we're gonna say, okay, ytrain.shape is 400 samples, and let's make sure the ytest.shape is 100 samples as well. All right, okay, so again, you have 400 for training, 100 for testing inputs, and 100 for testing outputs. Let's go ahead and perform the actual training using the support vector machine. So we're gonna say, okay, from sklearn.svm, we're going to import support vector classifier. And then we're gonna say, okay, from sklearn.metrics, we're going to import simply our classification report, classification_report, and we're going to import our confusion_matrix. All right, let's run that. Okay, looks great. And let's keep going and actually do svc_model equals to svc. Simply we're instantiating an object out of the svc class that we had before. And then we're going to use the fit method using the training data and xtrain and ytrain to actually train our model. So we're going to say, okay, svc_model, I'm going to say .fit, and I'm going to pass along xtrain, and I'm going to pass along ytrain as well. Let's run that. Okay, it's telling me there is a problem. My apologies, this svc. And here we go. The model is trained, looks good. Let's go ahead and actually evaluate our model. Let's actually delete this, delete that. Let's go ahead and do the predictions. So if you guys remember, we're going to do yPredict equals to, we're going to take a look at our model, SVC model. Let's grab that, paste it here. And I'm going to say .predict, and I'm going to pass along our xtest simply. That should give us the predictions if we insert a couple of cells. And we can use the confusion matrix, CM equals to confusion. So if we again do tab, it will should complete confusion matrix, and we can pass along our y-test, and we can pass along our y_predict, which is simply what we obtained in here. Let's run that, looks good. Let's do the sns.heat, again heat map. We're gonna pass along our CM, and we're gonna pass along our annotations equals to true. Let's run that, and here we go. Obviously the results are terrible, right? And as expected. So as you guys can see, we classified 43 points correctly out of class 0. However, we didn't classify anyone out of class 1. So we have 0 samples that have been correctly classified out of class 1. Let's go ahead and plot the classification or print classification report. So I'm going to say print, I'm going to say classification_report, and I'm going to pass along our y_test, and I'm going to pass along y_predict. Let's take a look. And here we go. We have 18% precision, which is really terrible. Okay. Obviously they were not, we're not happy with the results, but we know that we have 2 ways of improvements. First, we can actually scale the data. And the second improvement is to actually use a grid search to look for the best gamma and C parameters that will give us the best results. Let's recap what we have done so far. So what we have done so far is we have been able to prepare the data set for training. So we're able to basically obtain our data set in here for the bank data frame. We're able to do the train test split to actually split our data into training and testing. And we're able to use as well the support vector classifier to train the model. And we're also able to evaluate the model using the confusion matrix and using the classification report. In the next section, I'm going to show you how can we improve the model using the 2 strategies. I hope you guys enjoyed this lecture, and see you in the next lecture. Hello everyone, and welcome to this lecture. In this lecture, we're going to show you how can we improve the results of the model, okay, using 2 strategies or 2 techniques. So let's go ahead and do the first one, which is pretty much similar to what we have done before in the cancer classification case study. So first, we're going to do the feature scaling. So we're going to say, okay, minimum_train equals to x_train dot min, okay? And let's see that. That should obtain the minimum value. And then afterwards, we're going to say, okay, let's obtain the range. We're going to say range underscore train equals to our x underscore train, all the data points minus, we're going to subtract the min underscore train. So all the data points, we're going to subtract the minimum out of it, and we'll get the maximum value out of it, just the maximum range of the data. Let's run that, looks good. And let's go ahead and actually do the scaling. So we're going to say, okay, x underscore train underscore scaled equals to all our data point, which is x train. We're going to subtract the minimum value, which is minimum underscore train, and we're going to divide by the range, which is range underscore train. Let's run that, looks good. And if we take a look as well at x train underscore scaled, and if we do run that, here you go. So basically you'll find that the data has been normalized from 0 to 1, which is pretty much what we're looking for. Perfect. Let's make sure that we are on the right page. So let's go ahead and actually do the scatter plot. So actually that was going to be kind of a mini challenge for you guys. So I'm asking you to pause the video and please go here, plot or do the scatter plot between the age and 401k savings for X train, which is the original data, along with the X train scaled. So I'm looking for X train and X train scaled as well, just to make sure that the data looks exactly the same. However, the actual scale is different. One of them will be going to be normalized for this, and this one shouldn't be normalized. All right, please go ahead, pause the video, and I will see you guys after the challenge. All right, I hope you guys were able to figure out the challenge. So what I'm asking you guys to do is to use sns.scatterplot. And what I ask you to say, okay, x equals to, going to be our x train, and we're going to plot the age, right, versus our y equals to our x train as well. But here we're going to pass along our 401k savings. So I'm going to say 401k savings. And we're going to pass along our hue, we're going to be our y underscore train, right? And that's pretty much it. So let's make sure that everything looks good. So here we're going to pass our y train, and here we're just going to close this. All right, let's run that. Okay, there's an invalid syntax. So we are passing x equal x train, y equal x train 401k savings. Obviously here we didn't close that. So let's run it. And here we go. So now we have the scatter plot between age and between 401k savings, and you will find the data. This is pretty much the data that we had before. So to plot the normalized one, so we're going to do the same thing, but instead of x train, we're going to say x train scaled. And here we're going to pass x train underscore scaled as well. Let's run it, and here we go. The data looks exactly the same, which is perfect. However, the age is normalized between 0 and 1, and here the 401k savings have been normalized as well, which is exactly what we're looking for. Now we're pretty much ready to perform the training. But before we do that, let's go ahead and actually scale our testing data set as well. So I'm going to say, okay, minimum test equals to x underscore test dot min, because it should obtain the minimum values. And they're going to say, okay, range underscore test equals to, I'm going to say x underscore test. We're going to subtract the min underscore test, and we're going to obtain the maximum out of all this. Looks good. And afterwards, we're going to say, okay, x test underscore scaled equals to, I'm going to actually perform the scaling x underscore test, go to all the points of the testing, subtract the minimum, which is min test, and we're going to, this min test, and we're going to do that and divide it by the range underscore test. Let's run that, looks good. And we're pretty much ready to do the training again. Again, I'm not going to repeat it again. I'm just going to go ahead and copy it from here. These are all the steps, okay, to perform the training. So let's go ahead and copy that. I'm going to copy, go down here and paste it. So this is pretty much the same thing. We don't need to actually import them again, but it doesn't hurt. I'm going to say x train underscore scaled instead, and I'm going to pass y train as well. It's the same thing. Let's run it. Looks good. And let's go ahead and actually do the predictions, pretty much the same as before. We're going to say y underscore predict equals to, we're going to use svc underscore model, which is our train model, and we're going to pass along the dot predict method, if you guys remember, and pass along x underscore test underscore scaled. Okay, let's run that, looks good. And what we could do afterwards, we can say, okay, let's view the confusion matrix. We're going to say cm equals to confusion. Actually, we can do that, confusion matrix. We can pass along our y underscore test, and we can pass along y underscore predict. So on that, looks good. And I'm going to use SNS dot heat map, and we can pass along our cm, and we can specify our annotations equals true, just to view all our numbers on the graph. Let's run that, and it's much, much better. So if you guys can see here and compare it, you'll find that there are 41 samples that have been correctly classified, 51 samples that have been correctly classified as class 1, obviously, and here we have 8 samples that have been misclassified. If you go up and compare it to the previous results, you will find that here the results, obviously, of after feature scaling is much, much better. So here we have 57 samples that have been misclassified, which is really terrible. Let's go ahead and actually copy the classification report from here, and let's take a look at the classification report. And here we go. Now we have 92% precision, which is much, much better compared to the previous results. All right, and that's pretty much all what I have for this lecture. In the next lecture, I'm going to show you how can we improve the model, part 2, using the grid search and parameters optimization. I hope you guys enjoyed this lecture, and see you in the next lecture. Hello everyone, and welcome to this lecture. In the previous lecture, we walked you through how can we improve the model by performing feature scaling, and we found that we actually improved the accuracy or the precision from almost, I believe, 40% to 92%, which is great. Now let's take a look at another improvement, which is how can we do the grid search. It's exactly the same as we have done for the cancer classification case study. Let's repeat the exact same procedure here again. First, we're going to create our grid. So we're going to say, okay, param underscore grid equals to, we're going to say, okay, our C parameter, which is first parameter, we are going to try different values. Let's say 0.1. We're going to specify 1, 10, and 100. And for the gamma parameters, we're going to say gamma. We're going to specify, again, our parameters 1. We're going to specify 0.1. We're going to specify 0.01 and 0.001. And we're going to use the kernel of radial basis function kernel. Please make sure that the kernel here is this, and here we have RBF. All right. Okay, looks good. And for RBF, we need to make sure that here we have this listed this way. All right, let's run that. Okay, there's invalid syntax. Something is definitely wrong. So here we have our C, which is, these are all the C parameters. Looks good. Here we have our gamma, which is all, these are all the parameters. And here we have kernel equals to, we have our RBF. Simply, this shouldn't be equal. This should be colon. All right. And here we go. Let's run that. Looks good. So that's the first step. Second step, we're going to go from sklearn. We're going to import grid search CV as we have done before. I'm going to say, okay, from sklearn, we're going to dot model underscore selection. We're going to import grid search CV. Okay, let's run that. Looks good. And the next step is we're going to say, okay, grid equals to our grid search. Actually, autocomplete should do that for us. And then we're going to say, okay, let's instantiate SVC. And we're going to afterwards to pass along our param grid. And we're going to do refit equals true, so we can obtain the best parameters. And we're going to say, okay, verbose, let's say equals to 4, which is how many information do we need to plot as we actually perform the training. And then we're going to use our grid. We're going to use the fit method. We're going to pass along all our data, which is x underscore train underscore scaled. And we're going to pass along our y underscore train as well. Okay, let's run that. And here we go. So you find that obviously the score is getting better and better, 0.5. We reach 0.94, which is obviously better than the 0.92 that we obtained here in the past. That's good. And here we go. That's all our results. Looks great. So next step is, if we wanted to take a look at the best parameters, we can say, okay, our grid dot best underscore params underscore is when the c equals 10 and gamma equals to 0.1. These are the best parameters. All right, so what we could do, we can say, okay, let's take a look at the predictions. Again, if you guys remember, here in the grid, that's basically our objects. That's our kind of trained model. All the trained model, all the best models are contained within the grid. So you can simply go ahead and do the grid.predict similar to the model.predict as we have done before, or SVC model.predict as we have done before. I'm going to say, okay, grid.predict, and we're going to pass along our x underscore test underscore scaled. And here we're going to say, okay, this is our grid underscore predict. Let's run that, looks good. And now we can already to do the confusion matrix. So CM equals to confusion matrix. We can pass along our y test, and we can pass along our grid underscore prediction, grid predict. Okay, looks good. And then we can use SNS.heatmap, and we could do CM, and we can do annotations equals to true. All right, and shift enter, and these are the results. All right, is it better or worse? If you go up here, you will find that we have 6 samples have been misclassified, 2 samples have been misclassified. Here we have 6 samples and 1 sample, which means that, you know, kind of the optimization had made us improve the results just by 1 sample. We have been able to correctly classify 1 sample more, which is not bad. Afterwards, let's go ahead and print our classification report. We're going to say, okay, print. I'm going to say classification. So classification report. And we're going to pass along our y underscore test. And we're going to pass along our grid dot underscore predict. All right. And if we press shift enter, we'll get 94% precision compared to our 92, which is obviously much, much better. And that's pretty much how can we improve the model using the grid search. And that's pretty much, we're going to conclude our project for the bank customer retirement predictions. I hope you guys enjoyed that project. And let's recap what we have done in this project really quick. So in this project, we were able to classify mainly customers, either they are eligible to retire or not, using their input as age and 401k savings. And we're able to use the support vector machines to actually perform our classification. We went through data visualization, we went through the model training, and we found that if we just use the data as given, we find that we achieve actually terrible results, really bad results of around 18%, which is really terrible. And then we went again and tried to improve the model by performing feature scaling or by performing normalization. So we normalized the data, and then we found that we obtained around 92%, which is way better. And we have been able to misclassify 8 samples only out of all the training data, out of all the testing data. And then for improving the model, we found that as we moved out down here, we did the grid search. We found that the best parameters for C and gamma parameters, which are 10 and 0.1, and we're able to actually misclassify only 7 samples and instead of 8 samples, which is, you know, kind of 1 sample better compared to the feature scaling only on its own. And we have been able to achieve around 94% total precision, which is, you know, pretty good overall. All right, and that's pretty much all what I have for this section. I hope you guys enjoyed it, and see you guys in future sections. I hope you guys enjoyed this tutorial. Please subscribe to my channel for more videos. See you next week, and happy learning.